Hello, Daniel Abarski here. Today I want to talk about the very basic fundamentals of chemical kinetics, in particular monomolecular reactions, and how just derive from the very basic common sense principles how concentration of chemicals will depend as a function of time in case of monomolecular reactions. So let's look how it works. Imagine that you have a molecule A and it just reacts with time. And initially you have number of molecules, let's say Na, 0 initial time. So in order to describe what's going on with molecules, let's just introduce such a thing as P, probability to survive. Let's introduce it that way, and we'll see why it's useful to do it that way. Probability to survive at time t. Okay? So then what can we write now about Na, so number of molecules A, just as a function of t. So obviously it's going to be equal to number of initial molecules A and 0 times probability to survive, right? P of t, and that's why we introduced it this way. It's very obvious that this is the case. So what happens next? Next, let's see what happens if we ask a question. Okay, what is, let's first ask a question, what is probability of time t plus delta t? And this is basically, we introduced without derivation, but it comes from a very basic principle that probabilities of individual events are multiplied. So if there is a probability to survive during the time t, the probability to survive during time t plus delta t will be equal to probability, basically product of these two probabilities. So it comes from independence. It actually comes from basic probability theory, but for molecules it's quite obvious that it should work very well if events are independent of time. So okay, let's see what happens next. Now if you write that down this way, we can say that Na equals to Na0, and instead of Pt, well, this is correct. So now, wait, that's not what I wanted to talk about, sorry. What I wanted to say is this. I want to say, let's see what's going to be d delta Na, so change of Na. And it's obviously something, as we derive like this, Na of t plus delta t minus Na of t, right? This is Na of t. So, how are we going to derive it? Obviously, we're going to put Na0 in front of everything. And instead of, here we have probability of t plus delta t, which is the product of probabilities. So now it's just math. You don't think about it, you wrote down something that makes sense. You want to find delta Na. Why? Because that's what we're talking about here. We're talking about chemical kinetics, change in time. So minus Na of t, basically it's going to be minus P of t, right? So, which is going to be again Na0 P t, which is basically Na. Na0 Pt is Na times P of delta t minus 1. Okay? Kind of weird expression, but okay, why not? So what is P of delta t? Let's derive it first, and let's say, call it like a star. Let's see what P of delta t is, and in order to do that, let's just use Taylor series. So we're gonna say that it's P of 0 plus p prime, so first derivative, at 0 times delta t. So technically we should go further and further, but we're going to omit all other terms. And also, what is probability of 0? So probability to survive at time 0. Obviously this is 1, right? So we have from here that p of delta t equals to 1 plus p prime derivative delta t. So we now put that basically here, and this equals to na times 1 plus p prime 0 delta t minus 1. We have minus 1, and we have p prime 0 and a delta t. So yeah, what do we have here? We determined what delta na is, and if we put now delta t there, so we have delta na delta t, which is basically, you can say it's change of na with time, and this is equal to p prime 0 times na. So we now come into basically almost not yet completely, but to understanding of the chemical kinetics. So change of n with time, change of number of particles, in our case A, with time is proportional to the number of particles times some number. And to better understand this number, we just need to consider what's the general case. How do you think this probability in general case looks like? So if you have a certain probability to react with time, more likely it looks exponential. It just happens from our everyday experience, if you think about it. So probability to survive, more likely, let's call it E minus EKT. And so basically here, yeah, what do we have here? Here we have a derivative of the probability to survive at time 0. So we have a slope of this curve, it's basically the slope of this angle alpha. That's what determines the rate, and from, if you define probability this way, it technically doesn't have to be defined that way, but it's like a natural, very natural way of defining it as a constant, because that way this probability, this derivative is a constant, obviously, and you can see it equals to minus k times na. So yeah, if k defined that way, basically k is the reaction rate is minus negative derivative of the probability to survive at time equal to 0. And usually it's given in inverse seconds. So for typical monomolecular reactions, so K usually have actually dependence like that, minus E RT. We're not going to talk about it right now. It's some exponential factor showing basically showing the barrier of the reaction. But if we have a barrierless reaction, so E equal to 0, K0 pre-exponential factor of monomolecular reactions is usually of the order of 10 to the power of 13 inverse seconds. So basically it's usual frequency of the oscillations of the molecular bond, and yeah, typical pre-factor of monomolecular reactions is on the order of that frequency of 10 to the power of 13 seconds. So what does it mean? All of it means that you have molecules. What is monomolecular reaction? Monomolecular reaction is when you have a molecule and it just dissociates, or something happens with that molecule. Let's say molecule has two parts and they just vibrate in the initial state and then just dissociates once it just randomly happens. And that's why this basically rate it's independent of anything else except of this vibrational frequency of 10 to the power of 13 hertz. So it's typical pre-exponential factor. So yeah, that's what I wanted to talk about today. Very basic principles, derivation of the kinetic rate equation. So now we see that indeed from this very simple logic we have change of the, oh yeah, by the way, if you want to now from here go to actual concentrations, so A, that's how I write concentrations in parentheses, equals to NA divided by volume. You can from here see that you can easily have our typical kinetic rate equations where concentration, change of the concentration of A proportional to the negative K, rate of the reaction, times A, which is the concentration. So we derived how to write down kinetic equations for monomolecular reactions. Thank you for your attention. Please hit me a like, subscribe, and comment below what you think, what material should be covered. I'm just starting this, not even lectures, some sort of derivations of important and interesting fundamental topics in chemical kinetics, thermodynamics, quantum mechanics, and I really appreciate your comments. All of this is very experimental, and probably in the future you'll see a lot of changes with the way how I do things, but content is the most important. That's why I'm asking for your opinion. Please comment below. Thank you so much, and until next time, bye.